Thank you. We had a very wonderful panel yesterday, thanks to NVIDIA, the ADEC panel. But today I'm going to talk about our efforts both at Tokyo Tech and also at AIST. So if you're interested, come to those booths. AIST, Tokyo Tech, HPE, Fujitsu are our partners. Okay, so we're very interested in convergence of big data and AI. Okay, and also with HPC. And that's been on the horizon since the early 2010. We started research to really look at the problem. We have, at the time we had clouds that were very versatile, but not very powerful, not very scalable. They only handled the big data was a misnomer at the time because they only handle small data in practice. We had big supercomputers, but they were not very flexible. The batch queue, very static, and also the software stacks were not amenable. So we set out, doing research, how to converge the two, how to use HPC in order to accelerate the big data, and now with the emergence of AI, analytics using AI. And we had all these co-design applications to look at. After 4 years of research, we got a whole bunch of results, but I won't go into any of them because I only have 20 plus minutes. If you're interested, please look at the video later. Pause and you can look at what's going on. You can search for our papers. Now I'll give you very brief results of the co-design efforts and kind of characterize the workloads. So we had we had one team working on drug design. This is a real drug design, not something experimental lab. They're trying to design real drugs that'll counter neglected diseases like the Zika virus or dengue fever. Those that pharmaceuticals don't want to produce unless there's a very economical way of doing it. And using HPC and big data and analytics is one way to achieve that. So the team have been at it for several years. They work with pharmaceuticals and so forth. And from the HPC side, they get immense acceleration. For example, they do all kinds of stuff. That one thing they do with genomics, they developed with our help an algorithm called GoC, which is 240 times faster than the sort of like the usually employed tool like BLAST. And then with GPUs on an old machine, older TSUBAME 2.5, they get 70 times speed up. And then with parallelization, using their own tools initially, then by using some of the big data tools to parallelize, they get additional, they get scalability up to this full machine. So they get about 1 million times speed up over the state of the art. And, but they also do analytics. So they have various instances, and I won't go into details for interest of time, but to use analytical methods, machine learning, to also do drug discovery. So they have various means to analyze the experiments, analyze the simulations. So here the convergence of HPC and big data were happening. We also did a lot of graph analytics work, and this is unfortunately not on TSUBAME. This is on a K computer, or national flagship, and we've been #1 on the Graph 500 for the 6 straight editions, thanks to my very bright student who works at a certain company in Japan. But if you really want a big data AI HPC guy, you may go and recruit him, and the salary level must be a little high, probably. So this K computer, using our algorithm, is achieving 50% faster speed than the #1 machine on the top 500, which is the Taihu Lite. So, the Chinese are doing great on the top 500, but does it matter in graph analytics? Well, K is number 10, and it's 1/9 the speed of the Taihu Lite. They'll still get more than 50% speed upon graphs and graph analytics. Why? Well, because in graph analytics, it's the bandwidth of the interconnect, bandwidth of memory that matters. Flops has very little relevance in this context. So, and this is very evident in our analysis of the algorithm, where we do lots of analysis. Just give you some highlight, up to 65,000 nodes, we're using about 500,000 cores in the machine. With a very large graph, but 3/4 of the time is taken up by network communication. So on one hand, K has the fastest network in the world, and by the virtue of an algorithm that reduces the bandwidth requirements, two sides meeting each other, we get this number one result. Similar result in our co-design application doing weather simulation and assimilation with the with real-time data acquisition. So we get gigabyte per second and future terabyte per second sensor data coming in from observation from everywhere, including state-of-the-art radars like phase area radar. We're doing petaflops scale simulation, and we need to convert to somehow merge the simulation and this real-time signaling in 30-second intervals, 30 seconds. And the data rates, again, multi-gigabytes per second, future terabyte per second. We'll also need to transfer data to multi-terabyte per second, again, real-time in these simulation cycle. So, and then finally AI, we all worked on various AI, especially deep learning exercises. And here's my
We are studying how
colleague,
to precisely
Professor
identify
Shinoda.
various objects and their movements from video data. For example, to help improve safety from drive recorder video, we would like to detect pedestrians and their movement. We apply deep learning for this application. To date, we have used TSUBAME 2.5 for this research and have achieved the top performance in some international competitions.
Okay, have to stop the video here. But, again, deep learning requires significant acceleration via supercomputers, and in particular using GPUs. So when we analyze the workloads, there are two. In fact, when people say big data and AI converge with HPC, they think big data on one side and HPC on the other side, but it's not as simple as that. Because when you analyze the data workloads themselves, and in HPC you always analyze the workloads, it turns out there are two distinct types of workloads. One is analytics, graph analytics, sorting, hashing, symbolic processing, sort of classic AI. In these types of workloads, we handle very sparse random structures. Okay, so we need lots of bandwidth, and this is similar to HPC tasks that are more dominant. Sparse solvers, implicit methods, so forth. So, these are very synonymous. On the other hand, we have the new types of workloads represented by deep learning. And in deep learning, when you study these algorithms, you find that you do the dominant algorithm is using dense linear algebra, but in reduced precision. So double precision really doesn't matter, but single precision, half precision matters. So that's why on Volta you have the tensor engine to speed up the calculation. So these very distinct workloads, when we build supercomputers, this is also somewhat synonymous, dense linear algebra, but in reduced precision. And some HPC apps use reduced precision too, and they're becoming more dominant. We build machines to accommodate both. So the first approximation is when you build a big supercomputer with these in mind, then you get a very good big data machine. And that's why the cloud failed, because they didn't have this or that. But even deep learning, when you analyze the workload in more detail, you find that there are 4 layers of parallelism. There's instruction level parallelism, there's what's called a model and data parallelism, and there's a hyperparameter search. And it turns out that this low-level matrix multiply performance largely only matters at the very bottom level, the instruction level parallelism. When you go to higher levels of parallelism, it turns out they become bandwidth bound again. They become strong scaling problems. So at the very top, it's hyperparameter search, but even there, there are lots of stuff you have to do. So it's not as simple as just throwing a matrix engine that'll speed up your application, a deep learning application. So unless you do that, your speed up curve will tail off. So we did some analysis. We have a IEEE 2016 big data paper last year, in which we built a very precise model of performance model of deep learning. So this is not working on the algorithm itself, but we took several existing algorithms and then we built a very detailed, actually stochastic performance model for them. But it applies to across to most frameworks that are out there. And the result not only gives us very detailed account of what's happening, but also gives us the predictive power of what happens when we increase certain aspects of the system. So the baseline, this was taken with a prototype TSUBAME 3 machine, TSUBAME KCDL, which was using K80s, and using FDR as the network. It got a certain speed using 64 GPUs in the system. 64, okay? Now, what happens, if we're gonna, NVIDIA would be kind enough to give us new GPUs, and we can use FP16 on K80, okay, like Pascal. Then the expectation is you double the performance because FP16 gen performance on Pascal is twice that of FP32 performance. But it turns out using, there are slightly different optimal configuration that the model predicts, but largely with similar resources, it turns out that the speed up is only 22%, not factor 2, but only 22%. And that's because there are significant overheads in other aspects of the system, including communication, and most predominantly communication. And that's evidenced by the fact that when we go from FDR to EDR, so thus doubling the communication speed, we get 43% speed up. This is what the model predicts. Now, of course, you get the best of both worlds if you do both flops increase, but also the bandwidth increase. Then you get 58% speed up. Not factor 2 exactly, but you get close to that. So it really tells you that in all big data workloads, and also in scalable machine learning workloads, and you need scalability because you want faster time solution, because unless you do that, your training time takes like 2 weeks. People are not going to be very competitive, So you also need to have bandwidth in the system, not to mention other factors like bringing in data into the system, training data into the system, and so forth. So when we built TSUBAME 3 and designed to build TSUBAME 3, from the top level, it looks like a whole bunch of boring boxes, like boxes here, SCI now HP i6A, then OmniPath Fabric, and also DDN storage. The first approximation looks very boring. A whole bunch of boxes connected by a whole bunch of wires. Just an ordinary supercomputer, right? But it's a 12 petaflop supercomputer in double precision. And if you look at this, it's kind of built dense. But again, this really doesn't tell you anything. But if you really want to see the real thing, please come to the Tokyo Tech booth 363. But you can actually see this one. But the real design point in TSUBAME was not just to put together a whole bunch of GPUs and other components in the system, but to make sure, as I have said, to make sure there is sufficient bandwidth in the system and that you can move the data around at will with in a very succinct manner. So that's why, aside from the components, have the GPU, CPUs, and memory, you have the flash, and maybe we have Optane. It's still being planned right now. It's not there yet. And then you have the interconnect and OmniPath interconnect connecting the nodes. What we have done is to try to maximize the bandwidth and also to be able to have a switching network throughout the system. So, for example, the green is the NVLink, the blue is the OmniPath, and red is PCIe. Now, colors really don't mean anything, so it just happens to be green. To make sure that there are different links. But in reality, we really wanted these to be the same links, right? But right now the technology is we don't have some unifying links like NVLink with Gen Z connecting everything, so we have to use separate links. But firstly, when you look at the bandwidth, this is for Pascal. That's 20 gigabytes per second. This red PCIe is 16 gigabytes per second, and OmniPath is 12.5. So there's not that big difference, maybe less than factor 2. Moreover, there are 4 links here, so there's one link that can be assignable to each GPU using GPU Direct. And here, of course, the NVLink is essentially direct switch network, but we also put a huge PCI switch up here so that even the PCI is fully switched. So the result of this, the effect of this, is that any data residing in any parts of the system can be transferred without being blocked, up to the limitation of any link in between. An internode would be omnipath, but still 12.5 per GPU. And then up and down vertically, PCIe bus, it's switched, so you can move data around within a node. In fact, from any point to point, you can move the data around at full speed using sequences of RDMA. So there's a wonderful talk by Thorsten Hoffler, my very good friend and colleague, my research partner, talking about RDMA and streaming communication. So if you're interested, you can listen to that. But again, we have very high capacity. Not only have high capacity in each of the nodes, but we can move the data continuously throughout the system at 54 terabytes per second, or on an annual basis over 1.7 zettabytes. So people are worried about big data populating the entire, flooding the internet in zettabytes. But a single machine can theoretically move data at more than one zettabyte per second. Not a fairly modest supercomputer. So machine, you got 400 gigabit links, you got water, you got power. It just slides in. It's very compact. It's less small than one U server. We have a liquid-cooled NVMe because thermal throttling sometimes slows down the NVMe, so we liquid-cooled the NVMe as well for GPUs, CPUs. Everything else is also liquid-cooled. And it's put a lot of this, put a lot of efforts to co-design a system with them with HPE. We use all the modern data center facility technologies, water, cabling, power, everything's overhead. Whereas we reinforce the floor, we have over 1 ton per square meter of floor loading because water-cooled machines are getting heavier. So we don't have anything underfloor, no underfloor structures, but in practice we have everything overhead. And so here's a short video telling you that the nodes are aligned like that. But just like a good blade, it just slides in and out, just like that. And water, network, cabling, everything just attaches itself, all at once. So, okay, I have to skip the video because I don't have too much time. The PUE of the machine, the greenest, we have always, we won the Green 500 in our prototype machine. Well, it was a stunt machine, but we won it in 2013. We used that technology to basically achieve high PUE and also greenness in our production machine as well. So the PUE using warm water cooling is about 1.03. So only 3% for cooling, using 32 degrees C water for a machine. Well, if you use the storage, well, unfortunately we couldn't cool the storage with 32 degrees C water, so we have to use some cold water, which will elevate the PUE to 1.1, but it's still like 10%. Okay. So there's a computer graphics of the machine. This is the only way we can get the full view of the machine because the room is so small. It's just the machine is packed with the machine. We can't get this, bird's eye view of the machine otherwise. Okay. So, like I said, we won the Green 500 the last time as a production machine. This time we're like number 6, but that's fine because as a Pascal machine, we're still number 1, and moreover, we're a production machine. Okay, the real production machine at multi-petascale. So the AI capability of the machine is about 66 petaflops, including the older machine, and that makes us number 1 in Japan in terms of AI. Now, other institutions got interested, AIST in particular, which is the biggest national lab, industry lab, and they created what's called AI Research Center. And this is the director, Dr. Tsuji, and we got more than 40 FTEs there, and we also created a joint lab. Called the Real World Big Data Laboratory, or Open Innovation Laboratory, between AIST researchers at AIRC and researchers at Tokyo Tech, and the two machines that are AI and big data capable to study big data in HPC and HPC context. I said 2 machines. I mentioned that one. I haven't mentioned this one. So this is ABCI, our new machine. If you're interested, there's an AIST booth So I'll skip some of these. But AIST, basically we leverage the technology we had used, the design metrics and so forth for TSUBAME 3. We customized it more towards big data and AI. And then we built a new AI-centric supercomputer called ABCI. So in terms of the AI performance, with appropriate bandwidth, right? So it's not just pushing flops, but like I said, just like TSUBAME 3, we can move data around. With reduced precision by using Volta, over 4,000 Volta, we got 550 AI-Petaflops. Slightly smaller than the new DGX one, but that's fine, because this is an open system. Yeah. So this is the platform to accelerate joint academic industry research. And also, we use all the cooling technologies to make it one of the most efficient machines in the world. So there are lots of details. I'll flash them in case you're interested. You can watch the video later on. But again, 550 AI petaflops, but lots of capabilities to move the data around, lots of bandwidth, also software, big data and software, and high performance computing software stack convergence, and being very green. So in order to achieve that, we're building our own data center, a new data center, and we're making the data center open source. We're making the construction of the data center, we're making the operational practices of the data center, everything open source, how we cool the machine. Because our realization is for people to go to Google, say, well, I want to build this data center just like yours because fantastic results. Will they give you the blueprint? No. If you come to us, do we give you the blueprint? Yes. We will tell you how exactly we have built this. PUE 1.1, very cheap construction of data center, but the most modern data center in the world, etc. So contract's been won by Fujitsu. So there are, like I said, there are over 4,000 volts of the system, warm water cooling, etc. So compared to the older DGX1 box, it's about 3,000 times faster inference, 22 petabytes of storage, and of course we'll increase this. We also got some experimental places to put new accelerators, and we got currently 100 gigabit connectivity because shipping data in and out is important in collaboration with clouds. Because this machine will be used mostly by the industrial partners. So here's what the data center is going to look like. It only costs $10 million to put up, including a facility. We have a research building next door to it, but the data center will look just like that. Externally, we're not even occupying just 440 square meters or 5,000 square feet, not very big. But this 5.5 exaflop AI exaflop machine only occupies actually one rack, 2 rows. It's a very small machine. It only occupies about 36 racks. The storage occupies the other 18. And this racks and this space is for future expansion. Skip some of the details and just give you one or two slides in the interest of time. What we have done in order to procure, remember the figure I shown that I had the big data on the right hand side and AI on the left hand side to characterize workloads. For the acquisition benchmarks in collaboration with the vendors and in collaboration with our researchers and both big data and AI experts, we did exactly that. Our acquisition benchmarks are no HPC benchmarks, except maybe to spec to gauge individual CPU speed. But otherwise, no structural mechanics, no molecular dynamics, no QCD, no nothing. All our benchmarks were either big data, the ability to move things around, or varieties of machine learning workloads. And we had 12 benchmarks. All the vendors who are submitting, we had our own benchmark team. All the vendors submitting, of course they had their benchmark team. Everyone tried very hard. We got very good scores. These were not easy benchmarks. It was not easy, but the vendors went beyond our expectations. So I think this is really good. We'll make the benchmarks open source. We'll try to make the results open source as well, and see what other people will like. We'll also like to work with other people to define benchmarks for big data and AI. because benchmarks are important. On the other hand, if you have a wrong benchmark like the top 500, then it will mislead the industry. I'm sorry I have no time to talk about the software stack convergence, but I'll just flash the slide in case you're interested. You can come talk to me afterwards. We use virtualization not just for deployment of, for example, we use containers not just for deployment of software, but in order to actually segregate the nodes. Sort of like virtualization, but to segregate the nodes spatially so that we can have better utilization of resources and so forth. We do lots of things in the container space, not just to deploy stuff on the nodes. Okay? And we're also trying to use big data AI technology itself to control the data center. Again, we intend to make these open source so people can use, self-apply AI and big data techniques to get the best efficiency out of the data center. So we have projects to do that. So finally, 2 slides. How much efficiency do we get already with the hardware? Well, if you look at traditional Xeon data center, so this is not using GPUs, but Intel says 70% of the machine learning workloads are still done with Xeon CPUs. Okay, well, so how much can you do? So we went to various data centers, got the average configurations, not the top end, not the bottom end, average configuration, what the thermal requirements are, and so forth. And this is sort of like the average we got. Not, again, you can argue there are better ones, you can argue there are worse ones, but this is sort of like an average. Okay, so the average comes out to be something like on a per rack basis, maybe 30, 40, maybe 50 tera AI operations per rack. Okay. ABCI, TSUBAME 3, and both ABCI, and if we upgrade TSUBAME 3 Volta, if we get the money, will give us higher thermals, higher density, much more functional processor, gives us 17 petaflops per rack. So that's about nearly 3 orders of magnitude improvement on a per rack basis. 3 orders of magnitude. So you can make your data center 1,000 times smaller. But even if you can account for power, the power efficiency is still more than 2 orders of magnitude. So people who brag about 50,000 500,000 square feet data center, well, if you have an efficient one, maybe it can become 1,000 square feet. It's like an American home. Okay, shrink to the size of an American home. So we're on a trajectory. This is a very exciting trajectory going forward because I think big data and now AI is increasing in a very rapid pace, and we're trying to keep up with the innovations by building real infrastructures. And of course, these say flops, but we also, of course, building company data-centric features and bytes, both capacity and also bandwidth, and we told you about that. But starting from 2015, when we had a first prototype, this was a 1.4 AI-Petaflop machine. And we found one user was dominating this machine. 3 years later, by 2018, we'll have a data center that's half exaflop with, again, accompanying bandwidth. And, so this will go on. We'll have exascale machines in AI. True exascale, not limp pack exaflop, but true exaflop, truly useful exaflop. And what the National Artificial Intelligence Research and Development Strategic Plan put out by the White House last year said, to paraphrase what they have said, investment into the hardware, software algorithms, and the co-design for cutting-edge research infrastructure is absolutely necessary. And this is what we have done with HPC all along. If you had listened to the talk this morning with Steve Plimpton, there are some caveats in here and there and so forth, but he was also saying, there's sufficient investment. Machines are important. This is something that was somewhat ignored in the AI space. A lot of people are going to the algorithm space, which is good, but who has the infrastructure to accommodate them? Okay, top end, not just your desktop, but how do you get access to thousands of GPUs? Okay, to drive your deep learning science, drive your engineering, using AI and big data techniques. It's still not quite there. So this is our effort, and hopefully we can push on, and if you have any questions, please come and ask me. Thank you.